We're going to look at a reaction that we're going to run in class. It's called a thermochemistry lab. And I'm going to give you a little more background about one of the more difficult processes within this lab. It's a little bit confusing. So again, we will have talked about this in class, but this is an online version for you to look at as well. Let's begin. Let's look at the idea that if we had 50 milliliters of hot water, and when I say hot water, we'll say 70 degrees Celsius. And then I also have some room temp water, or close to it. I'll say cool water. And it's 20 degrees Celsius. And I take these two and I mix them together. You would expect the temperature to be somewhere in the middle. So add these together, you get 90, should be 45, ballpark, should be exactly 45 degrees Celsius. That's what we would expect. And I'm going to give that a name. I'm going to call that T average. T average. So again, how I did that is, or what I'm doing here is to add the values of solutions. And then I just divide by 2. So the average divided by 2. Easy enough. Now, a reality is that if I add these up, it may not add up to 45. Realistically, it probably doesn't. Let's say, for example, I add these two up and I get 44.7 degrees Celsius. It didn't actually work. So I didn't meet what my expectations were. And the question is, why? Why did that happen? Well, first, let's just give that a name. And we're not going to call it T average this time. We're going to call it T mix. And that's a value. And I'm going to call this observed. Value observed. I'll expand on this a little bit later, but we're going to call it just observed right now. Now, something else just to be aware of is when you measure a temperature of a water solution or a reaction solution, you're not really measuring the temperature of the reaction. You're measuring the temperature or the energy of the water. That's on the receiving end. That's the surroundings that you're actually measuring the temperature for. So based on the specific heat of water, the mass of the water, which you're actually measuring probably the volume of it, and then the temperature change. So whatever number this is, we can take it and take the opposite value and say that's what's coming from the reaction. So the reaction is equal to the opposite of the Q water. Okay. Now, something else that's in the mix here is as far as this difference in temperature here, that is going to be something we're going to call the air or the energy that's absorbed by the calorimeter. We're going to assign this energy difference between this 45 as what we'd expect and 44.7 based on what we observed. That difference in temperature, energy, is we're going to assign that to the calorimeter. So we're going to take a look at that. Let's say we have these two solutions. We add them together. And I'm going to say, again, we're looking at the water. And we have 50 mils, 50 mils. We have 100 grams of water. We have our specific heat. That's just a known constant value. It's got some units attached to it, grams and degrees Celsius. And then we have this change in temperature that we looked at. And we have these names. We're going to put those in here. We're going to say T mix minus T average, what we thought we would get. And they just so happen to be 44.7 and 45. If we put this together, this is the total amount of energy I remember the units are canceling out here, Celsius and grams, they go away. This is the total amount of energy that was unexplained, it disappeared, but we're assigning it to this calorimeter. So that's the energy that we're going to say is absorbed, Q cal. So in our case, 126 joules of energy was absorbed by the calorimeter in this process. Is that part okay? Of course, you can't answer me. I'm going to add one more thing to this. Based over a temperature range that we actually ran this. So we had really warm water, and the cup itself was room temperature. And we're going to say room temperature was 20 degrees. So the cup changed temperature over a period of time between what the cup was and the highest temperature average that it was. So you added these two in there, but as far as the cup is concerned, it never saw 90 or it never saw 70. It saw the maximum temperature, which is right here. That was the maximum temperature that the cup actually saw. So we're going to take a look and see, well, what did the cup calorimeter actually experience? So Q cal, that's this energy right here. It varied, or that was the energy that was observed based upon what we just discovered. I'm saying T cool. So the temperature of the calorimeter, really, room temperature. And let me go ahead and throw some numbers in here and we can talk. Or I can talk. 126 joules. That is the energy, again, that's unexplained. Over this temperature range, this is as high as the temperature got when I mix those two solutions together. And this is the temperature of the cup. So the energy that was absorbed by the cup over this temperature range. And if I do this math, what that tells me is that's the amount of energy absorbed by the cup for every degree Celsius change. So it takes this much energy to raise the cup 1 degree, not being like perfectly insulated and such. Okay, so what this does for me is it allows me to be a lot more specific when I'm doing that Q, pull this down a little bit, Q cal or QM cal, whatever you guys call it, a reaction when I'm looking at here. I can be a lot more specific because there's some missing energy, right? It's like, well, where did this energy go? I can now bring this into the conversation and be a lot more exact in my answer. So let's look at how this would play out. I want to look at a reaction. So Q cal, or Q reaction, excuse me, is equal to, and I'm going to look at two different things. The mass of the two solutions mixed together times 4.184, and again, that's going to be joules per gram per degree Celsius. This was mass in grams, times the change in temperature. Here we go. This is where we can become more specific. I can now take the cup into the conversation and say this is, again, the calorimeter value times what is that change in temperature. So the fact that I have this and a change in temperature would go away. I have joules. I can run this through the mix just like I did earlier, get an answer in joules, and get a final answer that is going to be in joules based upon what the reaction gave off. And typically we just throw a negative in here and say, yep, that's the energy that was released by the reaction or absorbed by the water, which we actually measured. We measured the water. Okay, I think that's probably good enough. Let me just mention one more thing here before I finish this up. Again, graphically, just to kind of show you where that T mix comes from, we'll look at temperature and time. We mix two solutions together, hot and cold, whatever it is, you get a reaction. And after 20 seconds and 40 seconds and 60 seconds, you take these temperature measurements, however, whatever time intervals you have. Your first temperature you find is somewhere like right here. And then your next one is right there, and so on. And then eventually you get yourself to like a room temperature. It just goes on forever. We want to know what the highest temperature is. So we're going to ignore some of these values. But I see that these are somewhat linear. We would extrapolate back to here. And this, using a calculator function, is really what we're after. That's Tmix. That's where that number comes from. Okay, so I think that's a decent explanation. If you have more questions, you can ask me in class.